Okay. All right. So yesterday I described for you some general aspects of just hydrodynamics. The various objects that we can construct from hydrodynamic ideas. And today, the point is to connect all that with integrable system and basically describe all these objects within integrability and get to GHD. So the first thing that we want to do is to understand these maximal entropy states. So remember that I was saying we have these states which are of the form exponential minus sum over I, beta I, qi, right? So some, where all the conserved quantities are being are involved in this exponential. Now, in integrable systems, there are different things that happen, but one thing, which is a crucial thing, is that there's an infinite number of such conserved quantities, right? So we have to deal with this infinite number of conserved quantities. Now, an important concept in the integrable system is that, writing this infinite sum as is, although it was done in the past. So for integrable systems, these are called the generalized Gibbs ensemble, because there's an infinite number of conserved quantities. Instead of a Gibbs ensemble, it's a generalized Gibbs ensemble. Generalized refers to infinite number of conserved quantities, let's say. So people looked at that in recent years and considered summing over a finite number of such conserved quantities. So taking some of these conserved quantities, perhaps the most local one, and then a bit less local, or something like that, and seeing if this can reproduce what happens when you try to thermalize a system. The system does not quite thermalize, but it generalized thermalize, let's say, and it should reach. So if you start with a state which is not far from the usual, which is not stationary, and then you evolve it in time, it should reach a state like that from the point of view of local observables. And this is okay, it's fine, but somehow you have to truncate, and you have to sum, maybe over a finite number of that, and it's approximation, and you're not too sure how to truncate and how to even organize a conserved quantity so that it can truncate in a meaningful fashion. In fact, people have studied that, and now it is, quite better understood how to truncate. But actually, it's not, it's not the most efficient way of doing things. In fact, this set of parameters, these beta i's, to some kind of coordinates for your state, it's not the most efficient set of coordinates. So there are other ways of representing the states which are more efficient, and that's the point about generalized hydrodynamics, is that you want to discuss states like that, but one point is that you want to discuss states like that, but you want to use coordinates which are a bit more efficient than these coordinates. And previously I was also introducing the average of the conserved densities, say of the local conserved densities. Well, that's another set of coordinates for your state, let's say. But again, maybe it's not the most efficient way. So there is a thing about finding the most natural and efficient way of parameterizing your state, and that's I think at the basis of this whole generalized hydrodynamic thing. And for that, to find these appropriate coordinates, we need to know a bit more about integrability, not just that there are infinitely many conserved charges is not quite enough. We need to know a bit more. Okay? And that's what I'm going to explain now. And the other thing I wanted to say, there was actually a question asked yesterday. So these charges, I kind of defined them a bit formally as saying that you can calculate this type of thing, qi of x over 0, and that can be seen as a bilinear form, and then you can think of that bilinear form as giving rise to some norm, and then complete the space with respect to that norm. You get a Hilbert space. So all this mathematical construction, and these QIs should be thought of as element within that Hilbert space. So it's a precise thing. And when you think of in these terms, then it's hard to make sense of that kind of exponential. But you don't necessarily want to make sense of this kind of exponential. So you can actually define more formally the space of states by using this kind of integrated two-point functions. What you see this as providing some inner product in some Hilbert space, and that Hilbert space is a tangent to your manifold of states. And then you can use that tangent to basically construct your state. Perhaps you take a flow from that point where you are towards the infinite temperature state, the trace state, which is nice and kind of easy to deal with. And that can be used to define your state. And when you do that, you don't actually need to write such an exponential. or to explicitly write these charges, you just need to consider Hilbert space properties, and you don't even need to know about how this two-point function exactly decay in space. It just needs, this integral just needs to exist. So somehow you can go a bit further, right? So you complete your space and you get something a bit bigger. And that's the point of choosing the right set of coordinates so that you get the big enough space that covers everything, because you actually, in principle, need the whole space when you do hydrodynamics, okay? So these are kind of comments, okay, I want to make. Now, how do you get to this right set of coordinates? So my point of view on it is that the most important concept behind integrability has to do with scattering. So there's a very well developed theory of scattering processes in gases in many body systems. And this is where you see the most clearly and most nicely the effects of integrability. And this is how you extract most nicely, I think, the coordinates for your state. So let me discuss the scattering map in integrable systems. And that will tell us, from that we will see objects coming out which connect very, very directly to the objects that Herbert on his talk considered, okay? So, so I would say, so in Herbert's talk, this was written as exponential with, there was a trace of lax matrix to some, sum over I, say, trace of lax matrix to the I powered times beta I. And then he was replacing that by some function, basically, and then using that function. So the scattering map and scattering consideration will make this type of construction, let's say, more general, so it can be applied to any integrable system, basically. Okay. So first thing is the scattering map. Now it's very simple. So this can be done in classical and quantum models. In both cases, the scattering theory exists and is interesting and is kind of relatively well developed. So, but let me just, for simplicity, think about the classical case and make comments for the quantum case. Okay. So I have a gas. Okay. So you can think of that as a gas of particles, but it doesn't need to be a gas of particles. It could be a chain of degrees of freedom. It could be classical or quantum. It could be a field theory. It could be many, many things. Okay. But kind of more simply gas of particles. And they are described by some coordinates, so positions and momenta, say. Pn, xn. Just thinking in the classical framework. So think, for instance, about the Toda model in this fluid perspective. And then what I'm doing is very simple. I'm evolving in time. Let's say that I evolve downwards in time for now. Evolving in time. So I have some configuration of particles at fixed time, so position and momenta. Okay. Now I'm imagining a map from this configuration to some other coordinates. That's the scattering map. And this map is constructed in a very simple fashion. All you have to do is take this particular configuration, and so maybe this gas was in some finite domain and all that, but then you forget about this domain. You just put it on infinite line, and then you let the particles evolve. That's what the map is. Okay. You let the particles evolve. So what will happen when they evolve? Well, they will go at different velocities, kind of separate and go a kind of way. And eventually, you have your gas of particles. Now I'm seeing it. I'm scaling it out a little bit. So there's this lot of particles there. And eventually, at very large times, you're going to have well-separated particles at specific momenta. You have a finite number of particles, maybe a large number, but finite number, and then well-separated particles, specific momenta. And so what are the momenta? So some asymptotic momenta, Pn infinity, basically. So P1, P2, P3. Now, if my particles were ordered like 1, 2, 3, 4, 5, like this, here they are not ordered 1, 2, 3, 4, 5 anymore, okay? But it's just labeling. I could choose the label so that this is particle 1, 2, 3, okay? And they also have, so for sure they have this nice, well-defined momenta. But there's another characteristic of this scattering configuration. And the other characteristic is some set of positions. So what are these positions? Well, if you look at this is kind of a straight line, right? This is the same momentum. Now, as you go towards, back towards where the gas originally was, because the particles, I should have, the particles the lines are not straight. You know, they interact with each other. There's a potential. There's all kind of things that happen. Okay. So if they actually interact, they end up somewhere. But if I just naively just take this line and extrapolate it all the way to the position it would be at 0, that's a characteristic of this asymptotic configuration. Okay. And I can write this as follows. I can say Pn as function of time will be some fixed number Pn infinity plus something that decays very fast if the potential that according to which the particles interact is exponentially decaying in space, then you would expect something that is exponentially small in time. So I write this is not necessarily, depending on the model, it might not be that, but some correction, right? While the position xn of t will have the form, well, certainly this momentum plus some shift, and this is this shift that I'm talking about. So these are called the impact parameters, I think, in scattering theory. So basically, if you kind of throw particles at each other, that you want to choose how their extrapolated trajectory would end up at t equals 0, that's the parameter of impact on that. Okay. So these are, now using that, we have a map, say S, I call it S, or I think it's S out, because you go from T0 to plus infinity, the out scattering map, which takes your PNs and your XNs and maps into your PN infinity and XN infinity. It's just formal map, just defined by the time evolution. It's very simple. Now, this map has different properties which are true, and this you can do integrable or not, by the way. So it has certain properties which are true, integrable or not. Model will be integrable or not. Okay, and so one properties is the following. So first property. Well, the time evolution, as we know, is in classical mechanics is a canonical transformation. In quantum mechanics, is a unitary transformation. So it preserves the canonical structure, basically. So if you choose a small little computation, you can actually convince yourself that a canonical structure is preserved on this mapping. And so, Pn infinity with Pm infinity is 0, as is Xn infinity, Xm infinity, where this commutator is Poisson bracket or quantum commutator, while Xn infinity with Pm infinity is, well, let me write just delta in M, in the quantum case would be IH bar, is just the canonical one. So just delta Xm. This is consequence just of this fundamental definition. So these are canonical coordinates, right? So it's a scattering map, scattering transform that brings you new canonical coordinate. The second thing is that if you look at the Hamiltonian, so suppose my Hamiltonian is, let me think in terms of a classical Galilean system, but the things can be done more generally. Suppose it's sum over n Pn square over twice some mass, so let's say mass equals 1, plus some potential, right? X sum over n and m, x f of xn, v of xn minus xm. Suppose the Hamiltonian is of that form. Now let me apply the scattering map on this Hamiltonian. Well, of course, the Hamiltonian is conserved, commutes with time evolution. So I can apply time evolution on that without changing the Hamiltonian, certainly. If I apply time evolution on that, according to this time evolution, particles get very far separated from each other and all this. So if the potential is a short range, that bit of the Hamiltonian will go to 0. So at very large time, this V, so if V is something like that, so it has some shape, so something like that, let's say, some confining potential or something like this. So that bit of the potential, when the particles are very far from each other and not interacting with each other anymore, should basically go to some constant when we can set to 0. And so if I do the scattering map on that, which is really just time evolution, right? What I find is that this it's an exact equality, right? This is equal to sum over n Pn infinity square over 2 plus nothing else. So you just do the infinite time evolution. So in terms of the scattering coordinates, of course, the Hamiltonian is very simple. So in other words, if I look there far in the past, what's the total energy? Just the energy of each of the particles. That's what I'm saying, right? It's not very complicated. So as a consequence, these scattering coordinates evolve in a very simple fashion. I just, they are canonical, and the Hamiltonian looks like free Hamiltonian on these coordinates, right? And so this scattering map trivializes your system, right? So what it says is that Pn infinity dot is 0 and xn infinity dot time derivative is just Pn. Right? Just it's simple change of coordinate that trivialize the whole evolution. So what you think is you have your system, your kind of system of particles there, you evolve it a little bit, and then apply this map on this slightly evolved thing, you get a new Pn infinity, xn infinity, see how they change, of course, evolve in a trivial fashion. Okay? Yes. Yeah. 0. Yeah. Yeah. That's right. That's it. That's okay. That's okay. I'm happy with that. So we eventually want to do a gas or a fluid or something that has a lot of particles on a large volume. And in fact, worse than that, right? I said yesterday, I'm taking this fluid on infinite space, right? I said, oh, my fluid cells are very big. I can just assume it's infinite space, right? So now I'm changing gear a little bit and say, well, okay, let me take it finite space, large but finite space, huge amount of particles, but still finite. And then this large but finite, there is still a lot of infinity, that I can still put. Right? Infinity is pretty big. And so I put this infinite space around it and then scattering map it. And then you have a zero density gas, if you wish. It's just these particles very far from each other. And that's a useful thing to do. And actually, this is something that will explain why you can do a calculation at zero density, for instance, a scattering calculation, and that still tells you about finite density gases. Okay? This is a kind of one of the important points. But so you can do that. For now, it's just a formal mapping, right? And I can do that and see what happens with it. Okay? Yes. Yes, exactly. So you're talking about the labelings and all that. If they cross the label, it gets all mixed up in all this. I will eventually, well, maybe just even right now, consider the label where I just look at the asymptotic particles and label them 1, 2, 3, 4, 5, and then there a lot of things can happen, right? Yes. Yes, exactly. This is yeah, exactly. Yes. And so actually about the labeling, so if you, depending what you are interested in, if you are interested in actual particle number 3 there and how it reacts, how it interacts with other things, with fluctuations and all that, then you do need to take into account this relabeling, and that is non-trivial. That's, I think, one of your papers. Indeed, that is non-trivial. But if you don't want to take into account this, then you don't need it and all that. So, but this is something, of course, that you need to put in, yes. Okay. What about the conserved quantities? So we said there's a lot of conserved quantities, like the trace of higher powers of the Lax matrix, and Herbert was talking about. Well, they are conserved, right? So point number 3, for the conserved quantities, they are conserved in time. So I can do the same type of arguments here and just see what happens very far in the past or in the future. This is future, I can do the past as well, right? And so typically, these conserved quantities, well, typically, in many cases, actually, you don't even know how to write them exactly, in fact. In the TODA case, you know how to write them out exactly. It's very nice. You have this trace of Lax matrix. But in all cases, what you do expect, and what you can see in this specific case, is that when you go to, when particles are very far from each other and separated by large distances, what you get are the conserved quantities of the free models. This is actually one of the principles of integrability. You check in various models and you assume that's probably true for all the models. In other words, you have a question that actually come back. You get that the conserved quantities, Qi, should be of the form sum over n, and let's say, for instance, in general, so if you have free model, what are the conserved quantities? The ith power of the momentum will be conserved and local and very nice. So these are your conserved quantities. And you expect that to be pretty general, not just TODA model, pretty general. Okay. Quantum classical. Yes, there was a question. Yes. Sorry, yes, Pn infinity, indeed. Yeah, so this is really, these coordinates, yeah. Thank you, yes. So conserved quantities should also have a nice form. And, yeah. Yes. By number of particles, yes. No. So I want finite density eventually. So length of confinement divided by number of particles. I will take both very large and finite number. Wait. So we have to be a bit careful. So here, this term non-trivial for sure, right? Finite, yeah, so non-trivial. But then I do the scattering map, which is just a time evolution. So I take that as a variable. I time evolve it, of course, this doesn't change the Hamilton. But inside, this becomes Pn of t, Xn of t, and all that. And at t very large, these are very separated from each other. And then there's no interaction when they're very large. So so at very large time, although we have finite density at very large time, since I'm putting this finite density into a vacuum, then density goes to 0. Yes, exactly. So there is the interesting notions here is that there's a gas finite density and then there's a vacuum. And I should point out what you choose to be your vacuum will affect what you get as asymptotic states and how you describe your whole thermodynamics. So if for example, you take a chain, not a gas, but an XXZ chain, classical or quantum, whatever, right? And then you say, okay, my vacuum is a House spin-up or something like that, right? Or it's the true vacuum for a given Hamiltonian. Right? And then you say in the middle, now I put some disturbance. This is my particles there. I put this disturbance on some large but finite size thing. And then I just let this quantum chain or classical chain evolve in time. What's going to happen? So people have studied that for TODA, for instance, TODA chain, right? What's going to happen? You're going to have solitons developing and radiations on top of that. So there will be this nice solitons with a bit of wiggle around it, solitons and radiations, and you can see that numerically. And this will be your asymptotic states. So not the free particles, but the free solitons. They're not free anymore, right? This interacting stuff, but the kind of freely propagating solitons with some radiations, which you have to describe. Yes. Yeah. Yes, maybe. Yeah, maybe my picture was not correct. Yeah, I'm not sure the picture, yes. Yes. So this is actually also a very good point. This was the trivial picture that I was thinking about. So it was not the right picture for the potential. It's a repulsive that I was thinking about. If you have an attractive potential, you can have bound state. And what does it do? It says that in your asymptotic coordinates are not just the position of the particles, original particles that you have, but you also have to give the position of these bound states and their velocities. And you have to see how many bound states can you form that are stable with this potential. And you have to characterize them all, give them so you're going to have an additional index, label for what type of particles you have. A free particle, a bound state with how many particles, what type of bound state. And for instance, with solitons, you can have these breeders. And they are asymptotic objects that can be long-lived and all that. So this is a non-trivial thing to do in many models. It's very simple in TODA, but it's non-trivial in many other models. But that's the kind of the scattering step. Okay, yeah. Questions? Yes. So the claim is that in integral models you have an infinite number of conserved quantities, and on the scattering map, it basically corresponds to seeing these objects as being kind of free particles or free objects of various types, and taking the conserved quantities for such free objects. Yeah, here's an integer, but then I want to go further. I say, well, okay, I want to do sum over I, beta I, q i's, right? And that will be sum over n, and some function, right? Some function of this Pn infinity, where the betas are basically Taylor series expansion. And then it's what I said at the beginning. Now I say, okay, well, so forget about this sum over I beta. So forget even about the i's, although I'm going to be using it still, but kind of, it's not really the right thing. The right thing is this. There's a function. So maybe I should write q sub w, like, functional, right? So it depends on the function. Given a function, you have your conserved quantity. And then the question is, what is the space of functions that corresponds to appropriate conserved quantity. And now comes the crucial point. This I can do integrable or not, right? I can always define these objects. I can always define them direct in the scattering regime, and they are conserved by construction for every function. So you would say, so I have not even an integrable model. And there's an infinite number of conserved quantities, and that's correct, because infinite number of conserved quantities, even if it's not integrable, right? But, I mean, kind of. It's like in a quantum chains, you can always diagonalize the Hamiltonian, if you wish. It's the equivalent in a scattering picture, okay? So, but most of them are not very good conserved quantities. They are not the ones that I can use as here, like integrate with the density and integrate and blah, 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 okay? So I have to see what are the good conserved quantities. And there, generically, you would expect that if you choose some generic function there, this is not a local conserved quantities in a generic system. But in integrable models, for quite generic functions, it will be local. That's the idea. Now I have to explain this. Yes? So they are this, and that's it, right? They are this. They exist, yeah. They exist in any interacting classical model. Yes. They are by construction. Yes, yes, yes. Why not? Right? You do the scattering map. You have finite but large number of particles. You construct this. This is conserved by construction. The Hamiltonian of this form, you mean? So for the purpose of discussion, I assume that the more general form, I mean, I don't know really what is the most general form where I can do this discussion in a clear fashion. I expect similar, like similar principles will hold there. Right? So generally, indeed, yeah. Highly non-local, yes, exactly. And that's the main thing. So I can always define them like that. But, this scattering map from the Px, this scattering map, or this one, Px to P infinity x infinity is highly non-local in general. Yes, okay, sorry. Thank you, yes, you're right. I abuse notation a little bit. Q tilde, yes, thank you. It is true, it is true. I said QIs are the local. It is not local anymore, yes. Other question? Yes, yes, really local, so attractive or repulsive local. Yeah, long range. Yes. Yes, yes, yes. And I don't know. So, if it's very, very, very non-local, in the end, you end up with, yeah, some, like if you have a chain with very non-local interaction, then you end up with something in higher dimension, right? So it's not, it can be infinite dimensional effectively, right? So if it's not too non-local but parallel decay, then maybe you can do something. And so there was a talk yesterday, in fact, about the various powers and all that, and supposedly this kind of analysis can be done here too, where you can, yeah, kind of try to define locality property appropriately. But I don't know what theory. Another question. Okay, so locality. So this is the crucial point. How you see is local. So the main point is that in integrable systems, there are two things related to each other. The scattering is elastic. And meaning that it preserves all the momenta. And it is factorized. Meaning that the many-body scattering process can be seen as a sequence of two-body scattering processes. Main property of integrability. In fact, so this is from beginning of integrability, people have found this or maybe assumed this and kind of work with this to get somewhere. Let me tell you why it should be the case that scattering is elastic and factorized. Whenever there exists at least one conserved charge, maybe one needs more than one in general, but at least in the simplest situation, probably one is sufficient. One conserved charge of this type with I greater than 2. I greater than 2. so, or maybe some function which is not p squared. Right? Okay? So suppose, this is an argument from Park in 1981, I think. The argument was done in quantum field theory, but it's a very general thing. Suppose there exists a local, and here I suppose there exists a local one, Qi, now I call it Qi, for some, let's say for I equals 3, okay, just for the sake of the argument. Okay? It's conserved, of course, by construction, but it's also local. So what I can do is simply, I can use it in order to see what happened with the full scattering process. So I have some particles there in, and some particles out. And sorry, now I changed my time axis because I'm kind of more used with this, but okay. Particle in, particle out. And I look at the full scattering process. So the full scattering is going to be S in inverse composed with S out, basically, right? It's a full scattering process, right? So you map to 0 time and then map to infinite time. So in general, something kind of non-trivial happens, so there's a lot of interaction, and then particles go out, and like everything can happen. Yes? Yeah, now, local Qi. I suppose the existence of one of them. Yeah, so let me, local, well, I just Q3, right? So, yeah, so I mean this one, so, okay, equal Q tilde 3, let's say. So I mean, suppose Q tilde 3 is local. Yeah, suppose, yes. It is non-trivial, right? But suppose it's the case, right? So the trick there is very simple. Since this is conserved, you can imagine the Hamiltonian flow generated by this conserved charge, like the Hamiltonian, okay? And you apply this Hamiltonian flow at 2 times and in 2 opposite directions, very far in the past and very far in the future. So you kind of apply E to the something like Q, this Q3, comma, blah, blah, blah. So just the Hamiltonian flow. And here with some time, say T3, and here with the minus of this time, T3, Q3, comma, something. Okay? When you apply this Hamiltonian flow, well, since it's conserved, you can bring the 2 lines all the way to time 0, and it doesn't. I think they will cancel each other. But you can take them far in the past and the future, so you get the same scattering process here. Okay? But then the idea is that when you do that, of course, you displace all these trajectories. No? Now, if I were to apply the scattering flow Q2, which is just Hamiltonian, I would displace all so when I'm far in the past or future, is just the momenta. The charge is just far momenta. So it acts trivially on the asymptotic momenta, but non-trivially on the asymptotic positions. Okay? If I was just doing Q2, it would displace them exactly the way that they move in time like that. So I would not do a lot. I would just go a bit further in time. But now I do Q3, so it displaces them in a different fashion. Instead of being proportional to P, the displacement is going to be proportional to P squared. So I displace them with a different velocity, which is the square of the momenta. I change the dispersion relation, right? This is what it is, right? So if I displace them with a different P's, so that means that they will now interact in different positions somehow, right? So they will not all meet in the position that they were supposed to meet, but in slightly different positions. The meeting positions will change because you displace them in a way which does not correspond to their natural time evolution. So if you had something like, just as an example, this, and then you apply this displacement like that, so you do this and that, what you get, after applying the displacement, you will have something like perhaps, so this will have gone this way, maybe this will have gone that way, maybe this one will have gone the other way or something. And so they will have moved, in different ways than their natural time evolution. If they move in different ways, if you do that for a large T3, eventually you manage to separate all the 2-body scattering space-time points. So you can take T3 so large that they're so separated that now the full scattering process can be described by a sequence of 2-body scattering processes. That's the main argument. One can put some more equations to that. That's the main argument of Park in 1981. You just need one conserved charge generically. You apply it, you displace the trajectories in a way that all the interactions happen at different points. And then you have this factorized scattering. So now in 1D, when you have just 2-body scattering with preservation of momentum and energy, then both momenta are preserved. Set of momenta is preserved. the particles can exchange each other, but the set of momenta is preserved. And so the set of momenta initially will be the same as at the end. This is elastic scattering. And the fact that you can write this whole scattering as a sum of two-body scattering, this is a factorized scattering. So there is, so if you look at, so this is the picture that Herbert talked about. So you look at the two-body scattering, you know, of two particles. Maybe they can exchange, they do all kind of things like that. Yeah. What I want to do. So two particles scattering. If I just look at two particles and nothing else, I look at the trajectories, the momenta are preserved and all that, but of course there is a shift we call phi of P1 minus P2. If this is P1, this is P2. This shift depends on the interaction, depends on the model, depends on many things, but you can calculate just by doing a two-body process, two-body scattering process. And then what I'm saying is that in this scattering process, this many-body scattering processes, the shifts of every trajectory is just the sum of these shifts for all the two-body processes that a given trajectory has kind of undergone. Yes? Yes, yes. I mean, I hope so. I don't know how to work it out precisely, right? But the idea is like that. The idea is that now for classical spin, you have solitons and radiations. You have all kind of things. And supposedly the higher charges act on these. So the Hamiltonian acts on the soliton by just displacing it as a free particle. That's why it's a soliton. It stays like that. But the higher charges displace it in a different fashion, different momentum. And supposedly it does not change its shape. It's still just displaced in a different fashion. It's because in the end it's the higher hierarchy in the same hierarchy of integrable models, but some higher Hamiltonian. So it has the same solitons and all that, right? And so I think the same picture holds, but I don't know the full workout of that. Yes. Yeah. Yes, yes, yes. Radiation. How you account for radiation? So supposedly you need to do some wave packets, and then something similar will happen. So you're going to have some groove velocity for your radiation and kind of wave packets. So, you know, when you do scattering of radiation, you've got to think in terms of wave packets. You still have to have them very nicely separated and all that. And when the wave packet come to your final volume, they become like radiations on a large space, but they start as wave packets. And then hopefully you'll be able to do that. So yeah, this first, yes. Yes, yes, yes. Yes, I don't know. That's a good point. Yes. Other questions? Okay, so this is the main idea of scattering integrable models, and the important thing then is the following. I was talking about locality. Okay? Now let me kind of push this idea a little bit further. So this is the full scattering. I want to push this idea a little bit further. And I want to push this idea so that it tells me about this scattering map itself, because that's what the kind of important thing. So I want to relate the P infinity to the P not infinity, so the X infinity to the X at time 0, okay? And the idea is that, okay, if you do the full scattering process, it's clear you start with set of momenta, you end up with set of momenta. But if you do partial scattering process, you start far in the past, say, and then you end up at time 0. Then there's a lot of particles, high density, and a lot of things, okay? So you cannot then identify very clearly all your momenta and all that. But the idea is that actually even within this finite density gas, up to finite errors, up to errors which are not too big, you can still identify one of these asymptotic particles somewhere at a given position. And how you identify it is just by summing over all the trajectories that they must have crossed. So you are there, you have this particle there, and goes somewhere, and then it crosses a lot of trajectories because there's a lot of particles in the gas, and then it ends up somewhere. You have a lot of particles, yes, a lot of other particles. But so you look at this particular trajectory is there, and it crosses kind of a lot of particles. It moves around kind of in various fashion. Then it ends up somewhere, and where it ends up, so the extension of this idea, where it ends up is written as follows. So it's basically so this is basically this xn infinity where it would have ended up, plus the sum of how the scattering shift has incurred in crossing all these other trajectories. So plus sum of phi of Pn infinity minus Pm. Maybe it's minus infinity because I look at the in scattering. Minus Pm infinity sum over m, where all the m is the trajectories that it has crossed. And this equation is kind of at the basis of everything, let's say. It tells you that you can map the position of these asymptotic particles, which you try to identify somewhere with a given momenta, asymptotic momenta, at time 0, so where it should be, right? And it's not a precise equation in the sense that you cannot actually follow these asymptotic particles, because when it starts interacting, the momenta change, the position change, a lot of things happen. It's just very far that you can identify again the momenta. But you can more or less follow it. You can more or less say, okay, where it should be. When there's these two particles interacting, after the interaction, this is P1 and this is P2. So I can more or less tell, say what's the right trajectory that I should follow. More or less, not exactly, but up to, say, some little O of 1 imprecision in a large system, which will not be too important, more or less it will be given by that. And this mapping from asymptotic far in the past to at time 0, which is precise up to O of 1, means that that all these other charges that I compute like that they are essentially local. Because then I can more or less use this mapping in order to see what the charge, which is here nicely well defined, would look like there. And because this mapping is up to O1 in precision, is quite local. So this is just words, okay? But you can make that, say, a bit more precise and then convince yourself that the result is going to be something that's quasi-local. That's more or less sitting around a certain position, okay? So that's the idea, this factorized scattering idea, which allows you to extract the locality of these higher conserved charges. Okay, so yeah, it's a bit more wordy, okay, but precise equations. That's my idea. Questions about this? Okay, so let me now construct. So there's one thing that we can do from this, and it's actually a very nice, beautiful thing, and is that we can now look at. Okay, so maybe I should say. So there was a question about the labeling of the particles and where they end up and all that. So here I'm going to use a labeling that follows this trajectory. So I start with some asymptotic particles, label 1, 2, 3, 4, 5, say, and then they interact with a lot of other particles, but I more or less kind of jump from particle to particle in such a way that at plus infinity I end up with the right momentum, with the right trajectories, okay? And there's a way of doing that which is not super precise, but up to O1 errors with that. And these tracers that jump from particle to particle, this is what I should call the quasi-particles of the model. And by integrability, these quasi-particles exist. Okay? So you can follow trajectories and jump from one to one, and so this is your quasi-particles. It doesn't exist if it's not integrable because you cannot do this process. But if it exists, it's integrable. Now, so remember that in the scattering coordinate, we have basically free particles. So these Pn, say minus infinity, xn minus infinity, they evolve freely. Okay? So they evolve freely, right? So now let me think of that in a naive fashion and say I have a gas of these free particles. I know what the hydrodynamics of free particles is, right? What's the hydrodynamics of free particles? What's the equations? Hydro or free particles? Just kind of particles that go around, and it's Liouville equation of preservation of phase space, basically. So here you have a Liouville equation for these. Okay? So I can think about the density of particles around certain point x, which will be basically number of quasi-particles at xn equal infinity. Actually, let me call this n to argue with my later notation. It will depend also on the momentum and on the position. Okay. And it's some density in the phase space. And that will satisfy the trivial equation that dt of n plus p dx of n equals 0. But this is phase space in the asymptotic region, right? Now I'm telling you that I can apply the scattering map to get to the real space. Okay? And so if I apply this scattering map, this S in inverse on this n, because of this nice kind of locality property, I get some new function, some let's say rho p now of momentum in x, but now this is going to be in real space. And the statement, which I want to say, maybe I don't get to it fully, is that scattering map inverse on Uville in integrable system, because of this nice change of coordinate, is nothing else but GHD. The generalized hydrodynamics for integrable system is actually the Uville equation. The asymptotic coordinates but mapped back to real space. And this mapping back to real space is local enough so that you can write a nice equation for that. This is the idea. Now, let me explain that a bit more. Actually, I'll go to kind of more complete construction, but essentially that will come back to this. Okay, any questions? Right, so yesterday I told you about, okay, we have the maximum entropy state, and then we have to construct all these objects in it to get to the GHD. So let me kind of follow this kind of roadmap and consider the maximum entropy state. So there is a relatively simple set of arguments one can make. So for instance, suppose I want to calculate trace exponential minus this charge QW, right? So that's what I want to calculate, right? So I can say, so in a classical setup, I can say this is going to be, say, sum over number of particles, integral over their position and their momentum. In the quantum will be the trace over the Hilbert space. And then I have this exponential minus sum over, well, minus this QW, okay, this conserved charges. Now this QW is written, you know, like this. So is this particular conserved charge, which is nicely written in some asymptotic coordinates. So let me do the scattering map. Okay, so then I'm going to have sum over the particles, integration over the phase space element, but the scattering map, as I said, preserves phase space elements. Right? It's a canonical transformation. So I have dx minus infinity, dp minus infinity, exponential, this charge, which I know exactly how to write. This is sum over n. There's a product of all these n of w of pn minus infinity. Okay? So if I apply a scattering map, which is just a transformation of coordinates and nothing else, this complicated looking integral, a priori, becomes a trivial looking integral, which is just integration over dx dp, something that just depends on p. Okay? So the scattering transformation really simplifies a lot this partition function calculation. So then you will say, well, that's it, I'm done, right? And I can just do the p integral. And it's like, it's a free model. So this is a free partition function, right? So the whole hydrodynamics is free, everything is free, right? Well, it's not quite the case, right? Where's the problem? Well, the problem is that I have this dx infinity, and I told you if I want to do the scattering transform, I have to start with some finite but large volume. So there's a condition on these x's there, something like x must be within something, you know, between 0 and L. Okay? And so I have a condition there that x must be between 0 and L. All the position must be between 0 and L. Yet I integrate over dx minus infinity. So I must relate the x infinity to the x, the real x, to constrain this x infinity in the right volume. So what does it correspond to? So I have this from 0 to L, all these real x. And now I look at the scattering map. And so there's a scattering map. And then in this kind of x infinity, so this is x, let's say, this is x infinity space, I must find the new volumes that corresponds to this volume at x0. And this is 0 from 0 to r. And that new volume is non-trivial. What is this new volume? Well, if you look at that, take this particle. Now I want to move it, say, all the way to the most left part it can go, and all the way to the most right part it can go, so from 0 to r. And I want to make sure that as I move it in here, it goes from 0 to L. So if I'm there, okay, so I won't cross anybody, but if I'm at R, then I will cross a lot of trajectories. So there's a change of volume, change of notion of volume from real from time 0 to scattering space. Change of volume, so you can write something like this integration for all these x's between 0 and L, product of dx infinity is basically this volume to the power n. And this volume to the power n is just obtained by this change of volume. And you can write the equation directly from that physical intuition that this is going to be the product of all the particles of L plus all the incurred scattering shifts. So sum m different from n of all these phi pn minus pm. This is the change of volume from the incurred scattering shift. And if so I can rewrite this as product over n 1 plus 1 over L sum m different from n of phi pm minus pn. And that now has putting that inside that integral, that partition function, allows me to calculate everything as integration over p. So I've taken away the integration over x. The change of volume, this r over L, is written as function of p. Yes. The what? So order of limit. Yes. No, but this is. But my parameter L was always there. I always had this finite gas there, then that I expand. And this, from there to there, is just a formal map, right? It's a transformation from there to there. It's just, it doesn't matter, right? I can have very high density, very low density. It's just a map, right? And whatever the density, there will be some scattering state. Sorry? No. So actually, this is important. Actually, this is a very important point that here, in the partition function, I constrain the x's. But for the scattering map, the evolution is unconstrained, is not constrained to that volume. There's a little bit of a change of your actual Hamiltonian, if you wish. Right? So here, this is, when I do the scattering map, is an infinite volume. It's just a formal mapping from coordinates to coordinates. While the physical thing, of course, is in a finite volume. And this change is crucially important, actually. So here, I just see that as coordinates, conserved charge, and put them in finite volume. But actually, when I want to do the scattering, I just kind of let them expand in infinite volume, just as a formal procedure, just kind of mathematical procedure. I'm not going to do that in the lab, cannot. This is in quantum. It would be a trace of a reduced space, but you would have to look at every one of these quantum configuration, and then insert them, embed them in a higher space, and do the scattering in this higher space. That would be the way to do. So once you have realized that you can change the volume from scattering to real, all you have to do now is an integral or a trace with things that only depends on the momenta, and you can do that. And then this is a large deviation analysis or the type of stuff we've seen actually in the talk yesterday and in the talk of Herbert as well. So mean field calculation, you define empirical density of momenta, and then you take the limit with large number of particles. You have to minimize the functional, and there's a standard set of computation you can do. Once you've done that, then it's kind of standard set of computation. Right? So with this standard set of computation, so kind of it's basically mean field computation. you define, so basically this 1 over L sum over n of any function, say function f of n is going to be written as integration dp, some rho of p. So rho, there was some p, I'm just going to write it rho of p times f of p. So you define a empirical density which should converge in that limit. So there's some rho. And then the average charges will just be integration dp, rho of p, and then some power of the momenta. You can take other functions, some function of the momenta. Okay? And so you know, from that integral, you kind of do this mean field analysis. You can also define this ratio of volume in mean field with this R over L. Actually, is usually denoted with quantum normalization 2 pi rho s, and that has a form 1. If I just look at that, 1 plus integration dp rho of p and phi. So this scattering phase phi of. So this will depend on say q, phi of p minus q. Okay. So this R over L is just coming from this, right? This. Taking the mean field version of that. This was R to the n, so you can just divide R over L. So 1 plus 1 over L sum, it becomes 1 plus integration dp. Okay. So these elements, so this rho of p and rho s of q, are kind of the crucial elements in crucial functions in generalized hydrodynamics and TBA. So okay, so once you do that, you do the mean field analysis, and you get something that is called thermodynamic Bethe-Ansatz, because it was obtained by Bethe-Ansatz originally, but can be written in classical or quantum systems independently. And what you obtain is the following. Okay? So you obtain that the free energy has the following form. So F will have the form integration dp, so there's normalization, here is the quantum normalization, times a certain free energy function that depends on something called the pseudo energy. So if you use this station, this is the free energy function. And this is the pseudo energy. Just names, okay, from the literature. And fine, you can write it this you know, it has no information whatsoever for now, right? Let's just write it that way. But the pseudo energy satisfies an equation. So epsilon of p satisfies the equation is equal to W of p, which is what was in that exponential there, what we have to integrate over. W of p plus with a correction, which is integration, say, dp prime phi by normalization, phi of p minus p prime. That energy function with that pseudo energy at p prime. This is TBA. Okay? So it tells you what the free energy is. Once you're given the function W, you put that in this equation. This is equation for, it's an integral, a non-linear integral equation for this pseudo energy, and then you put that in here, you calculate that. What is the free energy function? Well, in our calculation, we had classical particles, right? So what would be the free energy function for that case? It would be the free energy per unit energy of the free particle. So look, I was telling you here, if I didn't care about this, you know, x between 0 and L, it looks like free particles. I could just calculate the free energy there, right? So this is this F. This F is what appears there. So F of epsilon is basically exponential with a minus exponential of minus epsilon for you know, classical particles, such as the Toda fluid, for instance. Okay? And once you know that, you put that in here, you get the free energy. In principle, you get the full thermodynamics. The thermodynamics, well, the average conserved density. What is this rho and this rho s that I defined here, well, if you do the computation, what you realize is that df over the epsilon is going to be equal to rho over rho s. This is the particle density. So this evaluated at epsilon of p, okay, is rho over rho s as function of p. And this is something that I usually call, that I usually know by n. It is the occupation function. So this set of equations is the result of doing mean field analysis of that partition function. That's the reason. You do a mean field analysis, that partition function, you get this set of equations. So how it relates, so this is the free energy, so the log of that partition function. You do mean field analysis, you find the right distribution of momentum and all that. And what this tells you is that the right distribution of momenta is given by solving this nonlinear integral equation, getting a pseudo energy, calculating that, and obtaining this ratio for rho over rho s. That ratio, of course, rho s can be rewritten in terms of rho itself, so that is itself some integral equation for rho. Okay? And once you have that, you can also put that in here, and you get the exact free energy, and so all average conserved densities. Yes. So well, basically, this is supposed to be an exact result when you take. So here I was summing over L. So you take L to infinity, and yeah. So basically, L to infinity, N to infinity with a fixed kind of N over L ratio. Although here it was not an N over ratio. Here I had a chemical potential for the N over L. So I was not fixing N over L, just putting a chemical potential for it. And that should be exact in that limit. It's mathematically exact in that limit. Okay? Not complete proof, but it should be exact. Okay, so any question about the result itself? Yeah. Yes, that's right, yes. That part here, right? So what I'm saying, so this, in order to get f, you've got to know what that function is, right? What I'm saying is when I do this computation there that I've written there with the classical particles, the function that come out of this calculation is that particular function. Right? So it's not any f, it's minus e to the minus epsilon. So you put it, this is kind of property it's property of the statistics of the particle. It tells you it's classical particles. So the calculation I showed you, if I do it, what I'm going to get is not an f, is that f, that particular f in these equations. These are equations that Herbert wrote. He had this exponential minus epsilon. Does it make sense? But the calculation is rather general, and in fact, so what characterizes the model in this calculation? Well, of course, there's the differential scattering phase, characterize the model, okay, which is the scattering of these things. Of course, there is, so we discussed that there is also the possible set of asymptotic particles, right? Here, what you're saying is just these particles, but you might have solitons, you might have more things. And if you have more things, instead of just integrating over P, you have to sum over the possible things that you have. And then you have different scattering shift depending on the things that you sum over. Okay? So this integral over P is transformed into integral over P sum over J or something, right? Where you sum over the various things. And the other thing is this free energy function that characterizes the model or the particles that are involved. If the particles are classical in nature, then is that free energy function. But there are different possibilities, and in particular, if you have, so if you have, so this would be that. If you have a classical radiation, we're talking about radiation field, you're going to put log of epsilon there. So this is radiation. And when you put log of epsilon, this is a bit singular, you see, and then you get a UV singularity, the UV catastrophe that people found at the beginning of the last century, right? But so you have this here. If it's fermions, then what you will put there is minus log of 1 plus exponential minus epsilon. And if you get boson, you're going to put log of 1 minus exponential minus epsilon. And if you get anyons, you know what you write if you get anyons. It's basically the free energy for whatever statistic you have, having free particles for the statistics. So this is kind of the free particle bit, let's say. But it's modified because you don't put the actual W there, you put a modification of it, a modification by the scattering. Yeah, okay. So this is the general thermodynamic Bethe-Ansatz framework here. I didn't derive it with Bethe-Ansatz, but can be derived with quantum Bethe-Ansatz as well, where you get fermions or bosons. Can be derived in a classical fashion. It can be obtained in the TODA model from the trick that Herbert was using, mapping to Dmitry Edelman model, can be derived in various ways. And in all the models that I've looked at, which is not every model, but some big family of them, you always get free energy in that form, always. So a huge family of integral models have free energy which is in that form. It's quite general. Questions about this? Yes. Yeah, you've got to somehow figure it out from the model, yes. How you figure it out? Here, if I do the calculation, I find that it comes out like that, right? There's no ambiguity, right? But if I have an actual quantum model, I have to figure out what's the right statistic. So with Bethe-Ansatz, you find it, right? If you do some Bethe-Ansatz calculation, you can see that, okay, it's the right thing. Yes. Yeah. Yeah. Yes. 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 Yeah, but so classically, you will obtain the classical particles if you do I believe that's if I look at the equations, I do the TBA, the thermodynamics of the classical soliton gas. Not just I believe, I know. I think this is the right thing that you obtain. Yes, but we can discuss. Yeah, but okay. So maybe I'm wrong. So maybe again, but indeed, so the statistics is something you've got to figure out in an appropriate fashion. Yeah. Okay. What other questions about this? So the important bits that the ingredients are the scattering phase, which you can calculate just by a two-body scattering. There's the function W that characterizes your GGE. There's the statistics of the particles, which you have to figure out with appropriate calculation. Few body calculations probably sufficient. And once you have that, you put that in here, and you get your thermodynamics. Now, what about so this gives you all the average densities, which are essentially expressed in this way. Okay? What about the average currents? This is just the pattern. This is pattern functions, free energy, right? So how do I calculate the average currents? Well, I told you, recall, that there is free energy density and there is free energy flux. It always exists, these things. That generates the current. Okay? So maybe I can calculate free energy flux in a similar fashion, in appropriate fashion. And in fact, in order to calculate free energy flux, well here, because unfortunately, there is no calculation of free energy flux in such a precise fashion. It doesn't exist, so there's no complete derivation of free energy flux. But there are many good intuitive derivations. And one, I think, which is relatively nice is as follows. So we know that we have space-time, okay? And the conserved charges are integrated over space and we evolve in time. And the conserved densities are, these densities in space, and current represents how they change in time. But in quantum field theory, at least, there is a so-called crossing symmetry, where you can exchange space and time. And you get the same theory. You have to change some little things here and there. In fact, more than that, Thomas told us yesterday that you have this crossing symmetry beyond quantum field theory, right? You have them in these cellular automata. And it's probably quite a general property, actually. Probably there's some kind of crossing symmetry in a huge amount, in many, many models, okay? You've got to define in an appropriate fashion. But there's some symmetry. Now, usually, if you look at your system as being supported on a given x and evolve, on a given x slice and evolve along the x direction, it's a very ill type of model, right? There will not be Lieberman bounds and all kind of things. Nevertheless, it's it might still be, an evolution that you can write up and that you can do something like that. So if you take this seriously, certainly if you do the calculation in quantum field theory where things are relatively precise, what you realize is that by crossing symmetry, you get G simply by, since you exchange space and time, you get G simply by changing the measure of integration here. So instead of integrating over momenta, which represent kind of space, you integrate over energies, which represent time. Whatever the energies are, that's dispersion relation dependent. You have a Hamiltonian, you choose it, has a dispersion relation, so you integrate over its own dispersion relation. So you write G equals integration dp with normalization, and you write E prime of p, f of epsilon of p, where this is the derivative, this is the group velocity, dp of energy. Okay? And so this whole thing is dE over 2 pi is the energy measure. So what I'm claiming is that by crossing symmetry, all you have to do is change the measure and you get the free energy flux. And then it's just a matter of calculating. So you put that in here, you differentiate with respect to your beta i's and all that, and you get your currents. So you get you get the equations that were written previously in the other talks. Is that? And it's just a matter of algebra at this point, right? It's algebra with integral equations. So you get things like GI is going to be expressed as integration dp. There's some effective velocity that appears there just from the calculation, from the algebra, rho of p, and then say p to the power I, say. And this effective velocity is the one that Herbert wrote and that Jerome wrote before. So I think I need to write it. So crossing symmetry gives you the currents in natural fashion, and that gives out exactly the formula that were written before. Questions about this? Okay, so for sure this took a lot of time, right. So this is essentially then you get this equation. So if you then you write this. You write dtqi plus dxji is equal to 0. That's your equation. You put these in, so you have dt of integration dp, or let's say integration dp, dt of rho p pi plus dx of v effective rho pi, and all this is equal to 0. And then you say, okay, well, very nice, but this should be valid for all p to the all i's. In fact, more than that, right? It should be valid for arbitrary functions there, because I think I can take sum over i's with arbitrary coefficients and all that. So I could probably cancel this pi and write it as an equation for the momenta. So for these densities of asymptotic particles with this effective velocity. And that's the GHG equation, basically. Okay? So here you see it as emerging from calculating these QIs and JIs in this GGE, which you now parameterize in every fluid cell. You parameterize. You see, I'm not using the beta i's there, right? It's just not a good set of coordinates. It's just complicated. I'm using instead these rho that are defined as in that way. So these rho that come out from the TBA, which are in the end defined by this set of equations. And they are good characteristics of the state. In other words, knowing the W, which is the state, I can know a rho, but also knowing a rho, I can invert all this set of equations and get W. In fact, knowing N, I can also invert all this set of equations and know W. I have a whole bunch of set of coordinates for the state here. Either the beta i's, which are W, or the rho, or the N, which is this ratio, or even epsilon is also a good set of good coordinate for the state. Okay? And write these things in various ways. But here I choose the rho, and then I obtain directly this equation. Questions about this? Okay. So I want to finish with. I have a lot of time left. So with an example of how this GHD equation is very useful. And so I was saying, there are different coordinates, right? I can use the beta i's as coordinate. I can use the W function W of P, or I can use the rho of P also. And I can also use this N function, which I have introduced there, which is just this ratio of a density of particle over this rho S, which was basically the change of volume from asymptotic space to real space. Okay? And it turns out that if you use this N coordinate and work out the algebra again, you find an equation that's very similar to that. So you find that dt plus v effective dx equals 0. So you find that this v effective in the rho coordinate is inside the parenthesis, in the N coordinate is outside the parenthesis. And so you identify then this v effective, which comes out from TBA, as really the effective velocity from the hydrodynamic canonical description. Okay. So maybe I just, this v effective that comes out from TBA calculation of the current, in the end is identified with the effective velocities of the canonical hydrodynamic description. So the eigenvalues of the A matrix. Okay. And okay, so yes. So there are different things one can do. Let's see. So let me consider just as an application of GHD, because just I think has not been considered. It was the first thing that was done in the original papers. In fact, this problem was the origin of GHD. So why we decided to look at hydrodynamics of integrable system, and there was one problem that we wanted to solve, which had been solved in other situations, and it's the so-called Riemann problem. Riemann problem in hydrodynamics is the simple problem where you start, say, with a bath of hot fluid there at some temperature T left, and perhaps a colder fluid there at some other temperature T right. And you want to know, when you put these two baths together and let them evolve, what happens at large time. That's a problem that's been studied in hydrodynamics. It has, if you can study that using the Euler equation, so you can look at this as an initial value problem for your Euler equation, and just try to get the solution from Euler equation. There's a lot of subtleties about this. Euler equation does not have unique solution. You have to take the right solution to that, and there's all kind of a nice phenomenology. But if you don't think about that too much and do it in a naive fashion, you say, okay, what I'm going to try to solve now is this equation, either kind of this one or that one, with this initial value problem, which is initial value, where on the left you have a certain state, on the right you have another state. It doesn't need to be thermal, just two GGs. Okay? So I have on the left some WL, on the right some WR, and then I have also, say, well, rho L and rho R, or N L and N R. There are various ways of parameterizing my state on the left and on the right. And then I just have to solve this equation as a space-time equation. So how do I solve it? Well, this is relatively simple. You see the system, like in the literature on Riemann problems, that's why this is a nice problem, is relatively simple. The initial condition is invariant on the scaling, of course. This is a single point, so we can scale x. But the equation, the Euler equation, also is invariant on the scaling of x and t. So actually the solution, if there's no breaking of scaling invariance, should be invariant to the scaling. So I could write, say, my n as being a function of x over t. Of course, it's also a function of p, but as in space-time, with a function of x over t. We call this psi, or let me call this eta. To write. And so I just have to write this equation as an equation for eta. And what I find is, if I do the calculation, I find that the equation is eta minus v effective d eta of n must be equal to 0. And that's for every p, for every eta. So I find not a partial differential equation, but, well, it's still partial differential equation because there's eta and p, but there's a single variable that is being differentiated. It's just the eta variable. So what you see is that the whole solution will depend on the ray that you look at, and perhaps you have a kind of a change of temperature from right to left. And all you have to know is what is the state on these various rays. And then maybe you can analyze, is there some current being transported of heat, of temperature, of whatever conserved charges in these various states. Just calculate the current, the average current on whatever state that you have there. Okay? And that's what you want to find. Now, this is a very simple equation, right? I think you will agree with me. This equation has, for a given eta p, has two solutions. Either the derivative is 0 or eta is equal to Vf, right? There's no other possibility. And so that means that your n is going to be constant of eta everywhere for a given p, everywhere, except at some values of eta where it might change. And the value where it might change is it can only be given by this. So the solution that you write is as follows. You say, this is some constant when eta is smaller than V effective of eta p, and some other constant when it is greater than V effective eta p. And what are these constant in eta? Not necessarily constant in p, but constant in eta. What are they? Well, if I look at my initial value problem, what I have is that initially at time 0, I should have a state on the left and a state on the right. So if I go to eta to minus infinity, then this is corresponding to time 0 on the left. Eta to plus infinity is 0 on the right, time 0 on the right. And so when eta is minus infinity, t0 x negative, I should have the left state. If it's plus infinity, I should have the right state. So I'm going to put here n left of p, and here n right of p. And that's the solution, essentially. This is solution to this initial value problem in arbitrary integral models. Now we have to look at the solution and think about it a little bit. We will say, okay, well, this is this function n that characterizes the state, right? This is the normal modes that characterizes the state. And I'm saying that as function of eta, or maybe even as function of p, it has a jump somewhere. Right? So it has a jump somewhere given by this, right? But where the jump is depends on the effective velocity at that eta in p. But this effective velocity is a non-trivial functional of the state. Depends on the state. This was the formula that Herbert wrote. So it depends on n in a non-trivial way. So this is a non-trivial coupled set of integral equations. Effective velocity depends on n in a non-trivial fashion, really non-linear integral over p, and n depends on effective velocity as well. So how do you solve that? Well, I have no theorem whatsoever for is solution unique or what type it is and all that, but one can do this numerically. You can do this by recursion. You start with some effective velocity that you guess. You just take groove velocity, and you recursively put into this, calculate your n, from this calculate your velocity, calculate your un. And when you do the recursion, you get the exact state at every raise, and with this exact state, you can calculate the exact current, say at x equals 0 at very large time, for instance. Compare with numerics, and it works beautifully. This was done, so in the original paper on the XXZ model by Bertini, Colura, Donadis, and Fagotti. It was done, and they compare with TMRG. It works very, very beautifully. It was also done then with Herbert. We did that in the hard rod models. We did some also compare with numerics, and it works very nicely. And so this kind of works really, really good. Success of GHD. Yeah, okay, so basically that's what I wanted to say. Yesterday I told you about the C matrix, the A matrix, the B matrix, and all that. This can now be written explicitly in terms of the TBA solutions. There's explicit form for all these matrices. They're a bit more complicated, but was well actually Herbert wrote in his talk some of these things. So all the matrices, so the A, B, and C matrices can be written explicitly. I also told you about the 2-point function. There was this A, S01, O2 of kt can also be written explicitly. In many cases, you need to know certain certain objects which correspond to these local fields, but you use this whole formalism, you calculate, once you have J, you just have to do derivative, to calculate the ABC matrix. You do this derivative, you can put them together, and you get this also right quite explicitly. And that's it, yeah. Okay, yeah. So that's what I wanted to say. So thank you.
Since why one generally expects that the generalized hydrodynamics should fail at some order in an interacting system if the mapping holds so smoothly.
Yeah. So you mean like in the derivative expansion, basically?
Yes.
Right?
Why there should be
talk about, yes.
Yeah.
So it's good, yeah, good question. So so my expectation is that GHD should work. There should be a way of making this derivative expansion, which is valid, which is correct, up to infinite order. I think this is kind of a big statement, perhaps, but at least as an asymptotic expansion. So I think it doesn't fail even up to very large orders. But I don't know exactly how to work it out. Of course, you've worked it out in free models in all details. I suspect this can be generalized to interacting models, okay? And that should work. Eventually, it should fail because in this mapping, this scattering map, I was saying it's kind of local, right? You map from this position to that position, but you don't map it to an exact position. Actually, there's a bit of a small kind of a small small variation that you don't control just by the scattering. Okay? So which is O of 1 compared to system size, but which is still there. Eventually, that will make this whole thing fail. That's kind of my understanding. Which when you go to this small order, small scales, then you should need more information than just the conserved densities, basically. But that's my feeling about it.
So I understand that the complexity of this is as you mentioned, that the effective is a complicated functional of n or of rho of p. So are these functionals known explicitly, typically for these models, or what are these?
No, so typically you have to solve that numerically. That's I mean, typically you just have some complicated equation. I mean, of course you solve this numerically in a given state and you get the curve rather quickly. I mean, numerically you do get it.
So what should you solve numerically?
So you solve numerically these equations. So there's an equation for VF. It was written. There was one way which is where it was written is VF is equal to say P plus integration dq. There's a rho of q. There's phi of p minus q, and then there's a difference of VF. VF of q minus VF of p. So once you know phi, you know the model. Once you know a rho, because you know the state, if you know the state, you put that in here, you solve this linear integral equation. In fact, this is not the best way of writing it to solve it other ways, but this is actually linear, so you actually just have to invert a big matrix if you want, and you get the effective velocity. You have to know the state in phi. Now, of course, when you want to solve this equation, it's an equation for the state that involves VF, so you have to, again, do that in some recursive fashion. The better way is to use that one and kind of to solve, well, I think Herbert explained it, but you solve kind of linearly over some little, so as if this was not dependent on state and for so little time, and then you kind of continue with this. So that's the integral equation you have to solve. In the end, you can just write a big matrix times something there, and then it becomes nonlinear equation for n, if you will.
I just want to add one remark about the scattering map. I mean, so yes. I mean, I remember quite some time ago, I was very fashionable, and the field was chaotic scattering. And what they did is studied more or less the scattering map, but for a few degrees of freedom.
Yes, yes.
And what these people discovered, they wanted to look at non-integrable system and chaotic dynamics. And what people, of course, discovered is, you know, the scattering map, let's say for 3 or 4 particles. I mean, it's a very, very crazy map.
Yeah.
I mean, it's, you know, certainly not differentiable and who knows what. And the intuitive reason is the following. Of course, you're saying, okay, I take a repulsive potential. But then, you know, even if you have 4 particles, even if you take a repulsive potentials, I mean, you will have bound, I mean, not really bound states, but you will have bounded trajectories. Yes. Of course, when they're highly unstable, I have to sort of very precisely, you know, sort of tune my velocities in such a way that I get a trajectory which is not going into, you know, it's not a bound state in a quantum mechanical sense, right? I mean, where it's a real eigenvalue. Yes. These are just sort of, you know, particular trajectories in phase space, but, you know, there are many of them. There are, you know, infinitely many of them, and they sort of partition your phase space into things, and then each little region sort of, you know, the map looks different. I mean, so these are crazy functions, and of course, you know, I mean, you know, once you make it integrable, then suddenly these functions become very nice, and you know, one can work with them. I mean, I just wanted to point out.
Very nice, because indeed, I was, you know, one does that, and one thinks, okay, well, can we do this without integrability and see what the trajectories are and get some intuition out of this? So this is a very complicated problem, right?
Other questions? I had one question. So,
yeah.
So is this scattering experiment, is that a good way to check integrability?
Yes, I mean, if you can actually do it, it's the best way, I think. Okay. Checking integrability. It's not necessarily easy to do, right? So, but if you can actually, yeah, so you have your system, particles, whatever, you can actually send your particle through and see what they do afterwards. That will tell you.
The phase shifts and just see if they add.
Yes, for sure.
Satisfy the additive.
Yeah. So, but just in practice, I'm not sure. You know, given an actual model, like in the lab, like the cold atom model, for instance, very hard to do.
But in simulations, it's.
Well, yeah, in simulation, yes, right, yes, exactly. Yeah, that's right.
Sorry, I missed some points. Why is the low S? Why is the low S?
Rho S, well, yeah. So I raised it. The rho S, basically in the definition with the normalization I took, is phi rho S is by definition the ratio of I think was yes, the ratio R over L, which was the ratio of the volume seen in asymptotic space over the actual volume in real space. And that was written quite explicitly as 1 plus integration dp prime rho of p prime phi of p minus p prime. So it's functional of p, of rho, if you want. Functional of rho. So when I write this, you know, this is rho over 1 plus integration of rho times phi. So this is kind of a function of rho like this, and is a functional of rho. And maybe I should say one thing. So this rho S is, you know, it's kind of my notation, but it means essentially that it's the so-called space density. It's the density of actual available space for your quasi-particle to move with respect to the real space. So because of the interaction, they don't see the same space somehow. They see perhaps a bit more, perhaps a bit left, a bit less. So if they get stuck with the other particles, they kind of see a bit more, right? Because they get stuck there and then continue all this. So this is a ratio of space density. If you think in terms of the hard rod, where phi is just minus a constant, minus the length, this is just the actual free space that there is between the rods. So the rods occupy something, and there's some free space between them, and this is that ratio, right? The free space with respect to the real space. But it's a concept that is generalizable to these integral models. There is a ratio of space that corresponds to that. And in fact, I should say one thing. So the GHD equation is the application of scattering map to Liouville. But because of this locality, the scattering map application to Liouville is very simple, and what it corresponds to is really a change of the meaning of space. In fact, you can see GHD as emerging by defining a new coordinate, so kind of dx hat, by saying that my new coordinate is just, say, 2 pi rho s dx. And in terms of the new coordinates, the GEG equation trivializes to the Liouville equation. So if you have real coordinate and you say, well, now my space is not quite what I see there, but it's a bit less or a bit more, it's depending on this rho S, then what the equation you have to get for the density of particles in this new coordinate is a trivial Liouville equation. That's the change that corresponds to the scattering mass. So in other words, there is a change of metric that trivializes GEG equation just corresponding to this change of volume. It's just, of course, in the fluid, the change of volume depends on where you are. So it's a non-trivial metric. Right? Yeah.
Can you comment on? Because my understanding that this framework is useful, parabolic traps or some other is when the integrability is broken.
Yes, very good, very good. So, so that's of course an excellent question. What happens, right, when you're in a trap? So there is the way to think about it is as follows: think about just water in a trap, let's say, in some gravitational potential or something like that. You can still use the Navier-Stokes equation to describe water, right? I think everybody agrees with that, even though the trap might break momentum because it depends on on space now. That well, Navier-Stokes equation includes conservation of momentum as part of the equation. Like not quite conservation. It's a dt of momentum equals a force term, but it includes it, right? So we can likewise modify GEG to include a force term. Okay? So this has to do with force term. So the idea is that still locally at small scales, it's still all the charges are basically conserved now there. But at large scales, because of the external potential, there's a force that moves things around. And GEG with force term is writable quite simply. So there is dt rho plus dx df rho, and you just add one more term, a force term. So a dp because you change momentum, and there's an acceleration that comes into play, and this is this effective acceleration. The effective acceleration actually satisfies the same equation as the effective velocity. Is the effectivization of the bare acceleration. So AF will satisfy acceleration, which is whatever external force you have there. So you're going to have some derivative with respect to x of the energy, kind of the bare energy, that might include the potential and all that, px, plus the same thing, integration, blah, 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 where you put AF minus AF. It's the effective, it's the same type of equation, but with source term, which is acceleration instead of just velocity. And and this is what people use. You can also rewrite it in terms of the n coordinate where the v effective comes out, and also the effective acceleration comes out. And that's what, for instance, we use to compare with in the experiment with cool atom gases.
Yeah, so question concerning terminology. So one usually says there is a kinetic equation description, there is a reduced hydrodynamic description.
Yeah.
So now this equation looked to me as collisionless kinetic equation.
Yes.
Exactly.
Do
you agree with this or just?
Yeah. This is of course it was a comment that was made right from the beginning. In fact, the two papers originally took this two point of view. The paper of Bertini et al. Worked out a kinetic equation, while we worked out a hydro equation. We obtained the same equation. Right? So they are kind of one and the same, if you wish. It's yes. I mean, I don't know exactly how to fully phrase it. And of course, it was early on said, okay, this should be thought of as a collisionless Boltzmann equation, right? So Bethe-Boltzmann equation was the name actually that was proposed, so it's okay. I think the understanding is okay. Basically, it is a Liouville equation, on the scattering map. So Liouville is a kinetic equation, if you wish, and it's a simple change of Liouville equation. It gives that. But at the same time, it has interpretation as the Euler equation. I think this is just kind of an interesting part of it, that you can see this in terms of the theory of Euler hydrodynamics, and you get something that looks like kinetic equation. So, so maybe the kind of a possibility is that if you try to go to higher, so you have to be careful. So this rho of P is a density of quasi-particles, not the real particles of usual kinetic equation where you see particle interacting. This is kind of a bit abstract quasi-particles, okay? But probably if you try to go to higher and higher order in derivative expansion.
But when we say, right, for a thermal liquid a kinetic equation, it also would be equation for quasi-particles.
Yes,
so it would have roughly the same meaning.
Okay. So in the end, it's roughly the same. Yeah. So I was thinking perhaps if I go to higher and higher order, eventually the meaning of this quasi-particle density becomes more and more towards real particle density, and then you get something perhaps like Boltzmann or something like that. Okay. Yeah. But thank you.
I just want to make a comment because that's an ongoing discussion. Independent of names, one thing we agree, it's sort of, a function on one particle phase space, right? It's a function of position and whatever we call them. Let's them call velocities if I think kinetic theory. And that's evolving according to a nonlinear equation. But the main point is that if you do kinetic theory, you have a collision operator, and the collision operator produces entropy. So it's conceptually a very different equation. Of course, it's an equation and the same function, but conceptually, it's a very different equation. That's sort of simply
that's what's called collision-less kinetic equation.
What?
Collision-less kinetic equation.
Well, okay, these are free particles, right? Why to use sort of a name like kinetic or Boltzmann equation for things which are rather trivial, right?
I think I agree that, yes, one can see these. I also agree with Herbert. Maybe if it's Liouville equation, you can call Liouville equation collision as Boltzmann equation, but kind of Liouville equation. But it is, I think it is still interesting to understand that in a kinetic way as well, and also in a hydro way. I think both are interesting. To me, the hydro way, you see that there's a lot of theory. There's a ABC matrix. There is a two-point functions and all that. So the hydro gives you a lot, right? So the propagation of ballistic waves and all this. So at least for me, it was very useful to think of it in a hydrodynamic fashion. But I think the kinetic fashion is also interesting and probably also very useful.
Okay, so now if there are no other questions, let's thank Benjamin.